What's up, guys? Today we're going to cover everything that you learn in a physics degree. So I have a set of slides covering classical mechanics, electromagnetism, statistical mechanics, and thermo, as well as quantum mechanics, and then some special topics at the end. So let's get started with the first one, which is classical mechanics. So in classical mechanics, every undergraduate course basically starts off by talking about motion, perhaps constant straight line motion, and then eventually get to acceleration. So you're going to deal with things like projectile motion, and then eventually get to dynamics. So then what causes things to move? So you learn about forces, you learn about Newton's second law, how forces cause acceleration, and then you start putting these weird scenarios of blocks on planes, and maybe you attach a rope to them, and then it gets really weird. So you have Newton's second law always there to guide you. But eventually you learn that Newton's second law is, a vector equation. It's hard to solve. So maybe we can deal with some other things that are easier. So you learn about energy, conservation of energy, and how that can make problems easier to solve. Then you move on to learning about oscillations. So we know that things like pendulums or things like blocks on a spring, they go back and forth, right? So everything that goes back and forth can be described as an oscillation. Eventually, you talk about waves, but these oscillations can be all described with basically the same kinds of equations. So you deal with pendulums and masses on springs. And then you deal with these properties. Maybe you add some friction, there's some damping, and you start to figure out how exactly does the system evolve with time. And maybe you add a driving force. So maybe I'm pushing someone on a swing. So now I have the swing itself, I have the pushing force on the swing, but I also have some damping, some friction going on. So how does the swing behave with all of those things combined? Then you can start considering perhaps normal modes. So if I have two springs connected to one mass, or maybe three springs connected to two masses, how exactly does the system like to behave on its own? These are called normal modes, and then you need a lot of linear algebra in order to solve them. You also cover momentum. So momentum turns out to be conserved whenever you have some system, some isolated system without any external forces. So you can apply the principles of conservation of momentum to understand things like the center of mass of a system, or perhaps how collisions occur, like elastic or inelastic collisions. Now, eventually, you start talking about orbits, gravitational forces, universal law of gravitation, and how you can derive Kepler's three laws of orbits. So you can derive the first law, which talks about elliptical orbits. You can talk about the second law, which is about conservation of angular momentum. And then you can also talk about the third law, which is about the relationship between the distance to the massive star. So the planet is always at some distance to a big object like a star. And then how that relation is with the period. So there's a common way of saying it. The period squared is proportional to the radius cubed. Now, at some point, you also learn Lagrangian mechanics and Hamiltonian mechanics. So Lagrangian and Hamiltonian mechanics is just a cleaner way of doing mechanics, because then you start talking about generalized coordinates. You can get rid of constraints easily and focus on really what's going on in the system. So you can start doing Lagrangian and Hamiltonian mechanics. And if you're lucky, you go deep into the theory and you find very interesting relationships between Newton's laws and Lagrangian and Hamiltonian mechanics, and how at some level they are all equivalent, though not exactly. There are some ways where they might not be equivalent. Then you also cover things like rotational frames of reference, so non-inertial frames of reference, so you can learn things about the centrifugal force, Coriolis force, the Euler force, things like that. And then if you're lucky, you can learn about fluid dynamics, Bernoulli's principle. Personally, I did not take fluid dynamics in undergrad, so I didn't really cover fluid dynamics, but later on in life, I just learned it on my own. Classical mechanics, there's a lot more to talk about. This is just, scratching the surface of what you learn. It just put all together in one slide. So let's go to the next thing that you learn, which is electricity and magnetism. Now, this is traditionally a course on its own. You start off by talking about static electric charges and how they create their own electric fields. Then you move on to trying to write down that principle of creating electric fields in a way that is more general. So you talk about Gauss's law and how the flux through a surface is related to electric charges. Now, you also learn about magnetism. You learn about what creates magnetism. So there's magnets, but magnets at the end of the day are made up of tiny little magnets known as electrons. And you can apply Gauss's law to magnets, and you can learn that you can't have a single North Pole by itself or a single South Pole by itself. Magnets always come in pairs. They're always dipoles. And it turns out that currents create magnetic fields. So you also learn about the Biot-Savart law and how you can have a current generating a magnetic field. You also deal a lot with circuitry and circuit analysis. So if you're going to be an electrical engineer, then these are bread and butter for you. You talk about RC circuits, RL circuits, LC circuits, and at the end of the day, you talk about RLC circuits. So resistors, inductors, capacitors, and how you can put them together to create very interesting behavior. You can also analyze the Poynting vector, which is the transport of energy in whenever you have electric and magnetic fields present. So you also talk about the Poynting vector. You also talk about Faraday's law, so how a changing magnetic field can give rise to an electric field. And you also talk about how if there are wires with currents in them, then they cause forces between each other. Because we know that there's a Lorentz force on moving charges. So that Lorentz force between two currents causes them to either attract or repel. So at the end of the day, you can combine all of these equations, Gauss's law, Faraday's law, Ampere's law, and then Maxwell's correction, and you can put them into these nice forms of Maxwell's equations. So these are like the pinnacle of the class. Now, after that, you start learning about electromagnetic waves. And then there's a good chance that you'll talk about the multipole expansion, so how to find the potential of some weird distribution of charge on a sphere. So you can do the multipole expansion in terms of these poles, so monopole, dipole, quadrupole, octopole, etc. Once you deal with electromagnetic waves, then it's like a whole new area or class of optics. How does light behave? How does light refract? How does light interfere? Because it's a wave. So it's a lot of fun stuff dealing with interference, two-slit interference, diffraction, lenses, mirrors, all that fun stuff. All right, next up we have Thermo and StatMech. So in Thermo and StatMech, traditionally you just start off by talking about combinatorics, how if you have a collection of molecules and you want to count states, if you have so many different molecules, then you have to know, how many ways can I put these molecules that would look the same? And so you start talking about combinatorics, and that's the first thing you start off with in a StatMech course. So you can see here the combination formula as well as the the N choose R formula over here. And of course, you can use the Stirling approximation whenever you want to approximate factorials. This is a really handy approximation whenever N is very large. So in StatMech, you learn that there are 3 different ensembles that are used to go from StatMech to thermodynamics. You have the microcanonical, you have the canonical, and the grand canonical, so 3 different ensembles. And you learn how energy arises from the equipartition theorem, how you can go from the modes that energy can be stored in a gas, and how that translates into the partition function. So you can see here that molecules can have vibrational modes, they can have rotational modes or translational modes. So all of those can potentially contribute to your partition function. Then you move on to thermodynamics. So you go from StatMech and then you build up towards thermodynamics, the macroscopic scale. So you learn about 4 laws, the 0th law, the 1st law, the 2nd law, and the 3rd law of thermodynamics. And then you start applying them to various kinds of scenarios. So you can have, heat engines, Carnot cycles, how exactly is the most efficient engine built? What kind of process is this? Can you have constant temperature, constant volume, constant pressure, and so on? You also learn about heat transfer, convection, how if I bring 2 objects that are different temperatures and I put them next to each other, what happens to their temperatures over time. And of course, you need to know the state functions to be able to do all of these calculations. So these state functions are typically for your internal energy, your enthalpy, your Helmholtz free energy, and your Gibbs free energy. And they are related through these sort of Maxwell relations, as well as the Legendre transformations. All right, so next up you have quantum mechanics. So this is incredibly fun. You start off by talking about the wave function, maybe a little bit of probability, but the first example you deal with is the particle in a box. So you want to understand, where does quantization come from in quantum mechanics? So the simple example is you apply the Schrodinger equation to an infinite square well, and lo and behold, you have these modes of vibration that are quantized. You already get quantization immediately. N is equal to 1, 2, 3, 4 discrete energy levels. Now, it doesn't have to be an infinite square well. It could be some finite square well. So then you learn about tunneling, you learn about reflecting wave functions, transmitting wave functions, and just applying the wave function with the Schrodinger equation to different scenarios. Now you can apply the Schrodinger equation in 3 dimensions for a hydrogen atom. And what you find is something very interesting. You can predict what the shapes of these orbitals should look like in hydrogen. And that's perhaps the simplest case where you can actually solve the Schrodinger equation completely, and you get these very nice orbitals. So you deal with the quantum numbers like the principal quantum number n, the spin quantum numbers, J and or if you want L, before you get to J, you have L and M sub L, which is the magnetic quantum number. And then you have the intrinsic spin of electrons. So you have 4 different quantum numbers that you can start talking about. Now, this idea of spin is very mysterious. So you spend some time talking about what spin is. You can view it as maybe some vector on a Mobius strip. That's one way of viewing spin. And they are related ultimately to Pauli matrices, and it's called the special unitary group of 2 by 2 matrices, and they are described by these Pauli matrices. You might also talk about different kinds of statistics. So if you have bosons versus fermions, identical particles, how do you deal with the wave function of multiple particles? So that surely arises in a quantum mechanics course. Now, if you wait until the end and you have some time to work with it, then eventually you get to perturbation theory, which is kind of a technique of solving complicated problems in a simple way. The essential idea is if I have a really hard problem, I can imagine breaking it down into an infinite number of easy problems, and I just solve one easy problem at a time instead of tackling the hard problem in one go. All right, so this is quantum mechanics, incredibly fun. Lastly, I just want to end on special topics. So this is some things that you might pick up, maybe some laboratory techniques. So special relativity, that's the first special topic that there's no like one course where you learn relativity, just pick it up in different courses. You also learn some nuclear physics, nuclear fission, how much energy is stored, binding energy. So that's very interesting. You might learn some semiconductor physics, how you can have computer chips, how you can use silicon in order to control the current going through some materials. Now, if you take some particle physics in a modern physics course, you'll learn about the standard model of particle physics. So this is perhaps the greatest achievement of science to date. You might also learn about radiation. Of course, you will learn about radiation, so alpha, beta, and gamma radiation, and how you can stop those from penetrating certain materials. Some statistics, you will also pick up some statistics. So typically you're dealing with counts in a lab. So you're dealing with Poisson statistics. So it's good to know how exactly do I do the uncertainties? How do I propagate them? What kind of distributions am I working with? And finally, there's some lab techniques, how to use an oscilloscope, how to code, maybe in Python or C++, perhaps how to use an Arduino, and some fun experiments. So I hope you enjoyed this. If you're curious about perhaps majoring in physics or learning more about physics, I hope this is a first step of seeing what's out there, what you could learn. We're only scratching the surface. I've kept a lot of details out, but there's definitely a lot more to what I'm saying. So if you find this interesting, you found this fun, consider subscribing to the channel and think about maybe physics is something you want to pursue in the future. And let me know if you have any questions in the comments. Have a good one.